Thanks everyone for joining this week's Biogeochemistry Science Friday. Today we have Morgan Loechli, who's going to talk to us about some analysis she's done with aircraft observations. Take it away, Morgan.
Thank you, Forrest. Yes, thank you all for being here. Yeah, my name, like you said, is Morgan. It's Loechli. It's a difficult one to pronounce. I'm a recent graduate of the University of Michigan, and I'm really excited to talk to you all today about some of the research I did as a student with Dr. Gretchen Keppel-Alex, being funded by the Rubisco Science Team. And this was published earlier this year in Global Biogeochemical Cycles under the title Evaluating Northern Hemisphere Growing Season Net Carbon Flux in Climate Models Using Aircraft Observations. So for me, a lot of the motivation of this work comes from the fact that Earth system models tend to disagree on estimates of large-scale carbon fluxes. Here I've plotted the Access Earth System model in orange and the Community Earth System model in green. I've plotted here the average net biosphere productivity in the Northern Hemisphere in kilograms per meter squared per year for the years 2009 to 2014 for these two models. And we can clearly see, looking at this figure, that these models disagree on both the timing and the magnitude of this seasonal carbon exchange at the hemispheric spatial scale. So this highlights a need for some increased understanding of northern carbon fluxes, both so that we have an understanding of the mechanisms that drive these fluxes, as well as so that we have observations against which we can benchmark model performance. It would be great to be able to just make observations of these large-scale fluxes, but unfortunately that is not an easy thing to do. However, atmospheric carbon dioxide can be a useful tool in addressing that disagreement because atmospheric CO2 contains a lot of information about the sources and sinks of carbon at the Earth's surface. So within the boundary layer, specifically, the measurements of atmospheric CO2 are going to be a direct result of the fluxes at that location. For example, if we make an observation in a forest, you would see a stronger seasonal cycle than elsewhere due to increased photosynthesis in the summer months. In the free troposphere, however, the signals from these carbon sources and sinks end up being mixed together due to atmospheric transport, and we can make estimates of large-scale fluxes using only observations obtained in the boundary layer, but it's important that you know the winds if you try to do that, so that you know exactly where all of the carbon you're seeing came from and where it's going. One way that this is done is through the use of inverse models. These are models that adjust surface fluxes so that they best match observations of atmospheric carbon dioxide. However, unfortunately, these models have been previously shown to introduce uncertainty into flux estimates because of errors in simulating atmospheric transport. And so that brings me to a new data set, or relatively new, the HIPPO and ATom air flight campaigns. So these were flights that flew between 2009 and 2018, and they provide a new data set that can help us get around this problem of errors in transport simulation by having to rely less heavily on simulating transport. An example of one of the ATom missions is shown here in the figure on the left. It flew south over the Pacific and north over the Atlantic between about 80 degrees north and about 70 degrees south. The HIPPO missions flew over a similar latitude range, but both the southbound and northbound legs of the HIPPO missions were flown over the Pacific. Not only did these missions collect data over the ocean basins where the atmosphere is very well mixed, They also collected data vertically into the atmosphere. So the figure on the right here is showing the flight from Alaska to Hawaii, and the dips in the flight path show the dips in altitude that the plane made between about 200 hectopascal in atmospheric pressure, which is around 10 to 12 kilometers in altitude, all the way down to around 1,000 hectopascal in pressure, which is pretty near the surface. These observations provide us with a new constraint on the total amount of carbon dioxide in the atmosphere, because it has both that meridional information as well as vertical information about the structure of atmospheric CO2, which means again that we don't have to rely as heavily on accurately simulating atmospheric transport, because we have observations of what the structure of CO2 looks like in the free troposphere. So here is an example of some of that data from the HIPPO mission for the month of January in 2009. We're looking here at a curtain of the atmosphere. So the pressure is plotted on the y-axis in hectopascal, and latitude is plotted on the x-axis in degrees north. The coloring on this plot is the concentration of CO2 at that location as measured by the aircraft observations in part per million, and darker bluer colors are indicating smaller concentrations, while brighter and more yellow and green colors are showing larger concentrations. So we see that there's a lot of green on the right-hand side of the graph, and this is because the right-hand side is showing the Northern Hemisphere. In the winter months in the Northern Hemisphere, you have respiration and emissions outpacing land and ocean uptake, and so we see the expected overall increase in atmospheric CO2. This figure is also showing that atmospheric CO2 is greater further aloft, atmospheric CO2 is greater further aloft. And so we can see why having vertical information is so important. We see here that the CO2 concentration varies by as much as 10 part per million between the surface and the top of the observed region in the Northern Hemisphere, especially at high latitudes. We're interested here in land fluxes, so we're going to zoom in here on the Northern Hemisphere, specifically where there's more of the Earth's surface that is land, and thus we'll see greater variation in atmospheric CO2 due to land exchange. We consider latitude values between about 20 degrees north and the highest latitudes we have data for, which are about 80 degrees north. We cut off at about 20 degrees because further south gets into the tropics, which has a small to non-existent seasonal cycle, which would dilute the signal that we're looking for. We consider pressure values between about 1,000 hectopascal and 300 hectopascal in pressure. We cut off at 300 hectopascal because it's near the top of the troposphere, but also is the smallest pressure value where we reliably had observations from the aircraft. Within this region, the data is filtered to primarily remove takeoffs and landings, detrended to remove the long-term increasing trend in atmospheric CO2 due to increased fossil fuel emissions, and binned by 50 hectopascal in pressure and 5 degrees in latitude, so that there's enough data in each of these bins to fully constrain the seasonal cycle. We fit a second order harmonic to all of the data within each of these bins, and we see that this resulting seasonal cycle will look different depending on where in the atmosphere the bin is taken from. So the figure that's here on the far right of the screen shows the seasonal cycle of atmospheric CO2 in part per million in the bin that sits from 75 to 80 degrees north, and this is taken near the surface at about 950 to 1,000 hectopascal in pressure. We see a seasonal cycle with higher values of atmospheric CO2 in the Northern Hemisphere winter, and a sharp decline in the middle of the year due to increased photosynthesis during the growing season. The figure that's been added here to the middle of the screen gives us a picture of what is happening further aloft at that same latitude. So now we're looking at pressures from 350 to 300 hectopascal. We still see that there's a seasonal cycle, but the shape is different than what you see closer to the surface, and the amplitude is only about half as large. If we only had observations near the surface, we'd have a very different picture of what land-atmosphere carbon exchange looked like than if we only had observations at the top of this defined region. And so averaging this information together is what's so important because it gives insight into how the total amount of atmospheric CO2 changes over the course of the growing season. To aggregate this information together, we integrate all of these fitted seasonal cycles over pressure to get a column average cycle. And then we take an area weighted average over latitude to get the average cycle for the entire curtain of the atmosphere that we're looking at. So this resulting curtain average is the solid black line that's on this figure here. The red squares and the blue circles here are showing detrended average values for the northbound and southbound legs of each of the HIPPO and ATom missions. So you can sort of see here that integrating over pressure, taking the area weighted average and binning the data provides us with a slightly different seasonal cycle than you would get if you were to just take a simple average of all of the data. Now we want to be able to convert this concentration of atmospheric CO2 into a mass of atmospheric CO2 using the estimated mass of the atmosphere inside of the region that we're looking at. And then changes in this mass, so the derivative of the cycle, will give the flux of carbon into the atmosphere, which looks like this. So the black line on this figure here, which shows month of the year on the x-axis and flux in petagrams of year on the y-axis, are what we get after converting to mass and taking the derivative of the previous figure. The flux we can see is negative during the summer months, which again makes sense. It's indicating a net decrease in atmospheric carbon dioxide during the growing season. We see positive values in the winter months, indicating a net increase in atmospheric CO2. However, we need to further refine this estimate to account for any mixing of air in the atmosphere outside of the region that we're looking at, as well as any local influences on the observed CO2 measurement at any given location. So to do this, we do have to employ the use of inverse models. The orange curve that I've added to the figure here is the result of performing the same processing that I've just described, but using carbon dioxide mole fractions that were simulated by the Carbon Tracker 2019b model and sampled along the HIPPO and ATom flight track. There are some slight differences in the magnitude, but overall we see that this model agrees quite well with the observations. While it's hard to measure large-scale fluxes in the real world, it's a very easy thing to do in the model. So we can compare the flux that we estimate using the atmospheric CO2 concentrations from the Carbon Tracker 2019b model to the optimized land flux from that same model. We see overall that the structure is the same, with positive flux in winter and negative flux in summer. But we do see that the flight track derived curve, which is the solid orange line, has a different amplitude than the optimized land surface flux, which is the dashed orange line. Within Carbon Tracker 2019, we want these curves to match, and the reason why they don't is, again, most likely because of atmospheric mixing outside of the region of the atmosphere we're focused on, as well as local influences on the measured CO2 at a given location. And specifically in the winter months here, where there are large differences, this might likely be due to artifacts from fitting a second order harmonic and then taking the derivative of that second order harmonic. So by finding the differences between the dashed orange line and the solid orange line, what we're doing is finding the effect of these factors on the flight track estimated flux. And this then allows us to account for those effects on the observations. We do this with 3 inverse models as a way of trying to reduce the amount of uncertainty that would potentially be introduced by errors in transport simulation. However, somewhat surprisingly, the models show really good agreement at the hemispheric scale. So focusing in on these solid colored lines, we can see that they all match the solid black line pretty well. And this is telling us that the models are doing a pretty good job of simulating atmospheric CO2 concentrations that match the observations. All 3 of these dashed lines are also similar, which means that the posterior fluxes coming from these 3 models are similar at the hemispheric scale, despite the fact that all 3 of them use different transport models. So these similarities are showing us, firstly, that inversion systems are improving and doing a better job than we expected them to, but also that the inference of our flux is robust to the choice of atmospheric transport model used to complete this sort of correction process. Therefore, it's not imparting a huge amount of uncertainty into our flux estimate. So now taking those differences between the solid and dashed lines in the figure on the top left, averaging them together, and subtracting that average difference from the observations, we finally have our estimate of the observationally derived flux, which is the solid black line here in panel B. The dashed black line is what we started with, and you can see here that the overall pattern is still the same with negative flux in the summer. Additionally, the trough is now deeper, which is consistent with the differences that we saw between the inferred and posterior fluxes in the inversion systems. And the sort of artifacts in the winter months get smoothed out as a result of this correction process as well. We define the growing season to be the time during which there is a net loss of CO2 from the atmosphere, which is going to be when the flux is negative. We then integrate the curve over the growing season, which would be below the blue line on the graph here. And in doing that, we estimate the growing season net flux to be about 5.7 petagrams of carbon per year. Again, notably, this estimate is made primarily based on observations with very limited reliance on models, which is great. And we also were able to compare to some previous estimates that were made of the growing season net flux. We saw that they were broadly consistent with previous estimates, but it is somewhat difficult to make those comparisons due to differences in the time period studied as well as the methodologies used. And additionally, our estimate may not show an increase that you might expect in growing season net flux due to the observed increase in the seasonal cycle amplitude over the last 60 years or so. However, again, the differences in methodology as well as some large uncertainties in previous estimates make this conclusion unclear. Now that we actually have a metric for the flux, though, we want to use that metric to evaluate climate models. So here we have the Northern Hemisphere seasonal cycle of net biosphere productivity, which is averaged over the year 2000 to the most recent year available in the historical simulation for CMIP5, which is the previous generation of models on the left of the screen, and CMIP6, which is the current generation on the right side of the screen. Each of, oh, go ahead. Was someone going to say something? Okay. Each of the colored lines here represents a different model, and the thick dark line here is the observationally inferred net flux with its uncertainty estimate. We can see here that neither CMIP5 or CMIP6 models are agreeing perfectly on the timing or magnitude of the flux, but that is to be expected. However, looking at these figures, it does appear as if CMIP6 models have a reduced spread, as well as they're agreeing more favorably to the observations than the CMIP5 models do. So next, we want to look at how these models are comparing on the growing season net flux itself. And so we're going to build up this figure gradually. Each of the orange letters here is representing one of the CMIP6 models, and on the x-axis is plotted the start day of the growing season, which is defined to be the day of the year when the net flux first becomes negative. The y-axis is showing the growing season net flux in petagrams of carbon, which for the Earth system models is equivalent to total area-weighted average net biosphere productivity in the Northern Hemisphere, integrated over the growing season. I've added a dot here, which is representing the multi-model median. And the ellipse here is showing the two-dimensional variance to one standard deviation around the mean of the model ensemble. The blue letters, dot and ellipse, are the same for the CMIP5 models, and we can indeed see that the CMIP6 models are showing a decreased spread. The orange ellipse is smaller than the blue ellipse, but again, the question is, how do these compare to the observations? The black dot that I've just added here is the observationally inferred value for growing season net flux and start day of the growing season. And the gray bars here are the estimated uncertainty for these values. Somewhat surprisingly, the CMIP5 ensemble median compares more favorably than the CMIP6 ensemble median on both the start day and the growing season net flux, even though CMIP6 models seem to be doing a better job of simulating the seasonal cycle and have a reduced spread. So it seems like these CMIP6 models are agreeing better with each other, but they're agreeing on a slightly different value for the growing season net flux than is indicated by the observations, and a somewhat substantially different value for the start day of the growing season than what is currently simulated, that is indicated by the observations. So in general, the inferred growing season net flux from observations suggests that the flux should be larger and that the growing season should start later than what many of the current CMIP6 models are simulating. We are going to repeat this process, but instead of looking at the start day of the growing season, we're looking at the length of the growing season on the x-axis here. It's pretty clear looking at this one that most of the models evaluated here simulate a longer growing season than indicated by the observations, some of them as much as a month longer, which is a little bit surprising, especially because we see a negative correlation here, indicating that models that have longer growing seasons tend to have smaller growing season net flux values. This is a bit of a paradox because you would expect that if the growing season is longer, then there's more time for photosynthesis to happen, and so the growing season net flux should be larger, but that's not what these models are seeming to show, which may indicate that there's something off about the phasing of photosynthesis relative to respiration within the models. We also wanted to look at individual model performance as well by evaluating the absolute value of their z-score, which is a measurement of how many standard deviations away from the observations each model fell. Every modeling center, which had a model in both the CMIP5 and CMIP6 ensembles, actually showed an improvement in the newer generation. So we can see that with CESM, with CAN-ESM, with NOR-ESM, and most notably with IPSL, which went from being one of the worst models in the CMIP5 ensemble to being one of the best models in the CMIP6 ensemble. I think A few other notable things here are that the worst performing model across both ensembles is NOR CPM1, which is in the newer generation in the CMIP6 ensemble, and that we do have a few very good models, including the HAD, GEM, and the NIROC models in the CMIP5 ensemble that performed fairly well. And in general, I think this highlights the importance of evaluating both the ensemble as a whole as well as the individual models, because we can clearly see here an improved performance of CMIP6 models compared to CMIP5 models, even though the ensemble median for CMIP5 models performs better than the ensemble median for CMIP6 models when comparing to the observed growing season net flux. The growing season net flux is also dominated by land exchange, so we decided here to compare it to mean annual extratropical gross primary productivity on the left and mean annual extratropical heterotrophic respiration on the right, both in units of petagrams of carbon per year. Both GPP and RH show moderate to strong correlation with growing season net flux for the CMIP5 models alone, the CMIP6 models alone, and the combined ensemble, whose R values I'm showing on the figures here. These correlations allow us to apply an emergent constraint approach to estimate GPP and RH in the Northern Hemisphere, assuming that this relationship between growing season net flux and these gross fluxes is reasonable within the model ensembles. So the solid line that I've added here is the best fit line through both of the ensembles, and the dashed lines are the confidence interval. The intersection here of the observations with the confidence interval are what allow us to estimate GPP and RH. And we find that annual average GPP north of 20 degrees is about 56 petagrams of carbon, and annual average RH north of 20 degrees is about 25 petagrams of carbon based on this approach. Notably, the estimate for GPP is fairly consistent with the upper end of the range that's found using an ensemble of upscaled flux tower estimates. So those are all of the results. I do want to take a few moments here just to review all of the key points, and then we can open it up for questions. So firstly, we were able to use observations from the HIPPO and ATom campaigns to estimate net land atmosphere carbon exchange over the growing season, and we found it to be approximately 5.7 petagrams of carbon. This is pretty notable because, again, it was found primarily using atmospheric CO2 measurements. However, it may not show the increase that might be expected based on the observed increase in seasonal cycle amplitude. This observationally derived flux, however, does provide a good benchmark against which to evaluate model performance. We saw that the current generation of climate models show a reduced spread compared to the previous generation, but that the current models tend to underestimate the magnitude of the flux. They tend to start the growing season too early, and overall they estimate a longer growing season than the observations would suggest. These are important things for modelers to know as they interpret model results and continue to make improvements to the models, and we're currently in the process of getting this metric added to the International Land Model Benchmarking System. Lastly, correlations within the model ensembles allowed for the application of an emergent constraint approach to estimate average annual extratropical GPP and heterotrophic respiration. And we found that the estimate for GPP is consistent with the upper range of flux tower estimates, which may indicate that global GPP is also on the higher end of current estimates. So with that, I am done. I thank you all for listening. I will take a moment here to acknowledge the DOE Rubisco Science Focus Area, the HIPPO Science Team, the ATom Science Team, as well as all of the modeling teams, which I didn't have enough a space on the slide to list here for all of their work in making all of this happen. I will open it up for questions, but I do want to point out that if your question doesn't get answered, or if you just want to learn more, you can feel free to email me or to read the full paper. So with that, thank you. I will, I guess, turn the floor over for questions.